Hello, folks. Last week, yay! Well, for me, not for you. Okay. I want to wrap up our discussion about the central limit theorem and finish up the pollster problem that we started, in which we polled n people, or we want to poll n people, and find out what fraction of them believe in whatever. And the case study was how many of them believe that marijuana should be legalized. And we found estimates based on the Chebyshev inequality and a 1% accuracy. There was some confusion over this notion of accuracy, so I want to backtrack a little bit, make sure everybody's on board. It's possible I didn't phrase it properly. So let's say, so this is the pollster problem. Oh, I need a thicker pen than that. I need that. And this is today, what is it, 30 April? Okay. So, pollster problem. Let's say mu is the true fraction that believes marijuana should be legalized. Okay? Should be legal. And we want to estimate this. So we go and poll n people, and we ask each of the n persons whether you believe it should be legalized or not. And we want to estimate what mu is. So if ith person believes in legality and 0 otherwise. Okay? Now, in every poll we have an accuracy measure. So what we do is among the n people we pick, we add up the responses, so x1 through xn, which we represented with another symbol Sn, the sum of all the responses. Let's say if n is 1,000 people, let's say 650 people say yes. Then adding all these Bernoullis should give me the number 650. But then I want to estimate the probability. So using the frequency interpretation of probability, I divide by the total number of people that I've sampled. And this is my estimate of mu. What I want is for this mn, my estimate, to be between mu and some accuracy rubric. We started with 1% and then we relaxed it to 3%. So I want to be within 3%. In other words, if, say, the true fraction of the population that believes in legality is 75%, or 0.75 for mu, I want my estimate, mn, to fall somewhere between 0.75 minus 0.03, so 0.72, and 0.78. So that's what we meant. And we want this probability to be, and there's a confidence that we introduced, to be greater than or equal to whatever that confidence level was. I want to be at least 95% confident that the value I find for Mn is somewhere between mu minus 0.03 and mu plus 0.03. Mn, remember, is a random variable. So I have no guarantee that it will fall within that range. there is a possibility that it falls outside. I want to reduce that probability and cap it at a max of 0.05 or 5%. So that's what we mean. That's how the problem was set up. It wasn't that I was talking about 0.03 of mu. Maybe I phrased it incorrectly that time, or it wasn't very clear. So this is actually what we mean. So this is our confidence. I want to be at least 95% sure that the value I find for Mn experimentally falls somewhere between the true mean and plus and minus 0.03. So this is the accuracy level. Okay? And massaging this, we had the problem set up that we did, which was that I want the probability that Mn is away from the mean by more than 0.03 to be less than or equal to what? What? 0.05. Okay? So that was the problem set up, in case there was confusion over what we meant by accuracy and confidence. All right, so we solved this problem using first an accuracy of 0.01, and we found that we need a ridiculous number of people to poll to get to the answer we want, or to get the confidence we want. That was using Chebyshev's inequality. Then we relaxed the accuracy to 0.03, and we said it's okay if we're within 3% of the true fraction. 3% away from the true fraction. And that reduced our number by a factor of 9, but 50,000 divided by 9 is still too large. I think it came to about 5,600 people or so. And that's not normally what you see polls, that's not the population that you normally see polls polling. So then we said, okay, let's use the central limit theorem. So that's where we left off. What did the central limit theorem say? So the CLT said, suppose x1, this is one form of it that we're going to use, our IID, and we use the sample mean of this sample mean. We know that the expected value of Mn is what? If each of these has, let's say, xi is mu, and the variance of xi is sigma squared, what's the expected value of Mn? Mu. It was an unbiased estimator. And the variance of Mn was what? Sigma squared over n. That's right. So the variance, you can see right here, reduces as the sample size increases. Okay. So the central limit theorem says that, so one of the things I talked about last time was to standardize a random variable. This thing approaches a Gaussian behavior as n increases. But we only have one table for the Gaussians. So what we do is we standardize Mn. And the way we standardize is by doing what? I do what? Sorry? Subtract the mean. By subtracting the mean, let me actually explicitly say, this you can do with any random variable as long as its mean and variance are finite, which is the case for pretty much everything we deal with, although there are examples, counterexamples that you'll learn about probably in 126. So I subtract the mean. By subtracting the mean, I turn the random variable into a zero mean random variable. And then I want to standardize the spread. So what do I have to divide by? By what? Standard deviation of what? Mn. Whatever my random variable is. So take out the mean. And divide by the standard deviation. This should be your standard operating procedure for normalizing a random variable or standardizing a random variable. I don't like using the word normalizing because I don't want it to be confused with the Gaussian random variable. But in some literature, the term normalizing a random variable is also used. Okay. The central limit theorem says that the probability of Zn being less than or equal to some number Z as I increase the sample size will approach the CDF of the standard Gaussian, which is 1 over square root of 2 pi integral from minus infinity to z of e to the minus t squared over 2 dt. This is the CDF of the standard Gaussian. Okay? And I had a table for this. Let me find that table. Here we go. First of all, well, actually, let's do a little exercise. I want to make sure that you folks understand what. So let's take a slight detour. Here's my Gaussian. I'm going to plot it against t. So it's zero mean, and it's got standard or unit standard deviation, and I want to figure out what the probability is of this random variable being less than or equal to z. So this is the function 1 over square root of 2 pi e to the minus t squared over 2. Okay, it's symmetric, it's centered at 0, its standard deviation is 1. And I want to figure out, so the CDF is the area that I've highlighted here in purple or pink or whatever that is. So this is phi of z. What does phi of z look like? What happens? Can you talk to your neighbor and see if you can sketch this thing? Obviously, it doesn't have to be exact. But tell me what this looks like, which is the probability that my random variable t is less than or equal to z. This is f t of t. What does it look like? What is it when I'm at minus infinity? Where does it go to as I go to infinity? And how does it behave as I go from one end to the other? Rohan, my man. Even that's not enough for him. Need like cascade of amplifiers.
All right, I think we're all sick and tired of hearing my voice, so I'll use one of my passes to pass it to the
Notice how when he wants to pass, he's very loud.
To pass to the student in the gray hooded sweatshirt at
Well, go ahead and pass it.
of the right aisle. Okay. I think
You are?
Vlad.
Vlad.
Before, yeah.
Vlad is like a quantum particle. He was here the other day. Microphone. You turned it off.
Boom. Okay.
Okay, now it's on. Go for it.
So we're sketching the CDF, right?
Yes. I thought I picked blue here. Let's see. Okay. So where is it at minus infinity?
Minus infinity, it's a 0.
0, because there's 0 area when I'm at minus infinity. And then how does it be? And where is it at plus infinity?
At plus infinity, it should be at a...
What's the probability that this random variable is less than or equal to infinity?
1.
1.
Yeah.
This is true of all CDFs. Okay? And then as I move this z to the right, what happens to this area?
It increases.
It's increasing. And is it fair to say that for this particular PDF, it's monotonically increasing and it's smooth?
Yes.
Okay. Where does it pass the halfway mark?
At a mean.
At
0.
the mean. There you go. So it keeps increasing and it approaches 1. Okay? Cool. So the central limit theorem says that the probability, that the cumulative distribution function for the sample mean approaches this curve. That's what it says. It does not say that the PDF or the PMF of the random variables, in fact, the random variables could be discrete. But the CDF of that mean approaches this CDF. And I showed you a diagram last time. Let me pull that up. Uh-oh. Technical support. What do we got? Oh, there we go. No? Isn't this on? So. Oh, sorry, wrong hand up. Well, somebody wrote a book about me and called me a dung beetle. I need advice on what legal action I can take against this person. My kids get a kick out of this one. There we go, that's the right hand up. Okay, so this is the CDF. Notice if your random variables are discrete, you get that jaggedness, but that jaggedness goes away as you increase the number of those random variables that you're averaging over. Even though the PMF might not converge to that of a Gaussian. Okay, for a lot of them, even the PDF or the PMF will take on bell-shaped curves or approach asymptotically a bell-shaped curve. But for some, it doesn't. What does happen is that the CDFs start converging. And that's all we're saying about that's all the central limit theorem says. All right, let's go back to our problem. So now we have the situation where we have to determine the number of people such that, so let's go back to our problem. Give me the black ink here. There we go. So we want back to pollster. This is, oh, by the way, I didn't label this. This is the half mark. This is 1. This is 0. So back to pollster. So we want the probability that Mn is away from the true mean by more than 0.03 to be less than or equal to 0.05. This is what we want. The good news is that what I have inside the absolute value is already zero mean. The mean is already subtracted from Mn. So but the bad news is I still have to do one more level of massaging to get this into a form that I want. What is that level of massaging that I have to do? What do I have to do? Talk to your neighbor. Vlad, you get to pick the next person.
Hello.
Oh, God. Please.
Okay, she's not in a group, so I promised at the beginning that if...
We have to divide
You
by
are?
Parth.
Parth.
So you have to divide by the standard deviation.
Okay, so I have to divide by the standard deviation. Divided by the standard dev of Mn. And if I do it on one side, I have to do it
On both sides.
on both sides. Okay. Less than or equal to, does anything change on the right-hand side, Dev?
Nope.
Parth? Okay. So, then what I have is, what is this? Mn minus mu divided by? Remember the variance of Mn, you told me, was sigma squared over n. So, Parth, what's the standard dev?
It's the square root of that, so sigma over root n.
Sigma over root n. So I have sigma over root n is greater than or equal to 0.03 over sigma over root n. Root n can go here. Agreed? Alright, cool. And I want this to be less than or equal to 0.05. So I know that what I have inside the absolute value sign is actually a standard random variable, and I want it to be, I'm calculating the probability of it being greater than or equal to this thing on the right side of the inequality, and I want that probability to be less than or equal to 5%. What was sigma, Parth? Do you remember?
Not really.
Okay, I'll try to refresh your memory. The ith person says 1, yes, should be legal with probability mu, and says 0 with probability 1 minus mu. This is a Bernoulli. So sigma squared for this Bernoulli is?
I think it's like mu times 1 minus
1
mu.
minus mu. Okay? So if I think about this sigma squared as a function of mu, the problem is now I have this object here, which I don't know, in the denominator. So we seem to be in a catch-22. I don't know what that is, but somebody gave me a very nice answer last time. How do I bypass that problem? Yeah, I take the worst case scenario for sigma. So, what is the worst case scenario for sigma? So if I think about the sigma squared as a function of mu, this is a quadratic which I can plot. It's 0 at mu equals 0 and it's 0 at mu equals 1. Those are the two roots of my quadratic. It peaks at what value? 1/2. And at that value of mu, its peak value is 1/4. So this is sigma squared max. Okay. So I'm going to put the maximum value here. But let's first look at how things appear on the Gaussian curve. This is not quite in the form of a CDF, what I have on the left-hand side. That probability is not quite a CDF. So the central limit theorem says that this random variable Zn, its cumulative distribution function approaches that of a standard Gaussian. I am trying to figure out what the probability is of a standard Gaussian being greater than some threshold value. So, I guess before I should do something else. Before I do this, let's rewrite this as Zn. Well, let's look at the Gaussian first. I'll leave some space there. So here's my Gaussian. Okay? And whoops, that's not the... And I'm looking for the probability of a Gaussian random variable. That has to be symmetric. Boy, I'm on a roll here. This is one threshold. And the negative of that, I have to also mark. The probability that a standard random variable e to the minus z squared over 2 is greater than or equal to this threshold is given by some area. How would I talk to your neighbor and tell me, or to explain to each other, how I would highlight this probability on this Gaussian curve? What would that correspond to? If I want my random variable, z, to be greater than or equal to this value in magnitude. This threshold obviously is a positive quantity. N is positive, 0.03 is positive, standard deviation is positive. So how would I mark that on this PDF? Parth, you should be thinking about picking somebody else.
Okay.
Okay. Who's your pick?
I'll pick this guy.
Hello.
Hi, you are?
Matt.
Matt. Go for it, Matt. Tell me which areas to shade. Or
Like
area.
The left and right extremes.
Left. Sorry, that was right. Left and right. That purple area, the sum of those two purple areas is the probability we're looking at. That's not quite in the form that I can use a Gaussian table for. So how would I convert this to something that I can read off easily from the Gaussian table? That's the question. So let me do a generic diagram here. Here's a standard random Gaussian, which has the generic form e to the minus z squared over 2. It's got the bell-shaped curve. And I'm looking at some quantity alpha and minus alpha, and I want to figure out these two areas. How would I convert this into an expression involving the CDF? Can you do the algebra on the diagram? Talk to each other. I want something in terms of the phi, capital Ph's. Okay. Matt, can we continue with you?
Okay. Or do I get to choose someone else?
No. So I'm asking if you want to continue with answering the question. You had it easy last time.
Okay, it's just like 2 times phi of the one of the sides, yeah.
So 2 times this one, right? So probability that z is greater than or equal to alpha is 2 times the right area. Okay? Now, can you express that area on the right in terms of the CDF?
Phi of 0.03.
No, forget about plugging stuff. We use alpha. This is a generic problem. So, what is the CDF of alpha, at alpha? Can you tell me what area that would be? The probability that, so the CDF at alpha is the probability that z is less than or equal to alpha, correct?
Oh, yeah.
Okay. But that's not what I'm asking, what we're looking at, right? The area on the right is not that. How is the area on the right related to this? It's 1 minus. So it's 1 minus the CDF at alpha. Okay? That's what enables you to read from the table. You have to convert it to the CDF of the standard Gaussian. Okay. So, now, any questions on this? You gotta get comfortable playing around with these areas. So if I want, what if I wanted the area between, what if we want to calculate probability that Z is between alpha and minus alpha. Then what? So there's my Gaussian. Here's alpha. Here's minus alpha. This is actually a question that you more often will come across. What's the probability that I'm within, say, 2 standard deviations of the mean? If I measure my alpha according to the standard deviations. So, what is that probability? How would I express that in terms of the CDF?
Just like 1 minus the previous expression.
1 minus the previous expression. So, it's 2 phi alpha minus 1. Okay? So, what I recommend is that you play around with problems and get comfortable and fast with doing these kinds of manipulations. If you want to figure out the probability that a Gaussian is between a certain number and it's negative, then this is the kind of area you're computing. If you want tail probabilities, this is the kind of area you're computing. Sometimes you want the tail probability at one end and not the other, sometimes both ends. But from the diagram, it should be fairly straightforward to get. All right. So now we are looking. Let's go back to our poster problem, and we're looking here at the tail probabilities. Let me use a different color now. We want this probability, the sum of these two tail probabilities, to not exceed 5%, 0.05. And we said, let's use the worst case scenario. What is the worst case scenario? That I use a value of sigma that brings these boundaries inside or outside. The worst case would have boundaries here and here, or here and here. Which one would it be? Talk to your neighbors. It's important to keep these straight in your head. I want the tail probabilities to not exceed a certain amount. If I bring the boundaries in, would that increase the tail probabilities or not? So if the increased value is less than or equal to 0.05, is it true that my actual value is less than or equal to 0.05? So the worst case scenario is the sigma that brings the boundaries in or out. In. And in fact, that's what happens when you pick sigma max. So this is 0.03 root n over sigma max. I'm dividing by a larger number, a larger value of sigma. Yeah. Question? Because then it becomes a chicken and egg problem. Because I don't know how confident I can be in my MN. That's what I'm trying to figure out. So I can't count on it at this point yet. So then this one would also be minus 0.03 root n over sigma max. Now the areas I'm looking at are these green areas. Okay, now the tail probabilities. If I ensure that the green areas sum to something less than or equal to 0.05, then I'm guaranteed that the purple areas sum to something less than or equal to 0.05. Is that clear? Excellent. So now I know what my sigma max is. My sigma max is what? Well, I know. Do you know? What is sigma max? 1/4? 1/4. Well, if it's not 1/4, then what is it? 1/2 Please, don't mix up the standard deviation with variance. The maximum variance is 1/4. The maximum standard deviation is 1/2. So what this means is that now I'm going to clean up my diagram. I'm going to redraw it. So here's my diagram. Here's my Gaussian. And I'm now looking at 0.03 root n over sigma max minus 0.03 root n over sigma max. This one is, so sigma max is 1/2. That's as if I've multiplied the 0.03 by 2. That's my boundary here, and this is my boundary on the left side. And I'm looking to minimize, or to ensure, oh, I need green, that this area and this area, so sum of green areas, sum of green areas must be less than or equal to 0.05. Now I've bypassed the fact that I don't know what that sigma is. I took its worst case scenario. As I increase n, what happens to the tail probabilities? Decreases. So the inequality I get, is it n greater than or equal to something or n less than or equal to something? Ultimately, I have to get an inequality for n. Greater than or equal to something. Okay? All right. So what did we say? We said we want the probability that Zn is greater than or equal to 0.0. So our pole problem now has translated into this. I want to see the probability that my standard Gaussian random variable is greater than or equal to 0.06 root n. I want this to be less than or equal to 0.05. This is the CLT translation of our Polster problem. So we subtracted the mean, we divided by the standard deviation, we took the worst standard deviation possible, and this is now what we have to compute. And you told me earlier that this probability, the sum of these two tail probabilities, is what? Notice this? Huh? This is the formula you have to use. Where alpha is now 0.06 root n. This is your alpha. So the probability that Zn is greater than or equal to alpha, where alpha is equal to 0.06 root n, you told me is equal to 2 times 1 minus the CDF at alpha. And this has to be less than or equal to 0.05. Okay? What inequality do you get for phi of alpha? Can you work that out? You got to do some of the work here. Talk to each other. Figure out what the inequality is for phi of alpha. And then we will go to the table. That's our last step. Now that we've translated everything in terms of phi of alpha, there's only one step left. Once you have that final inequality for alpha, we will go to the table. And you will read off the value and we'll solve for n. Alright, I'll take a volunteer for this one. Phi of alpha must be what? First tell me if it's a greater than or less than. Greater than what? 0.975. And since the tables are usually in 4 digits, I'll put that. So if you carry this inequality to its logical conclusion, you will arrive at this inequality. So now the question is, what value of alpha corresponds to a probability that is at least 0.975? So this is my Gaussian. This is my alpha. Phi of alpha is here. I want this area to be at least 0.9750. What is the value of alpha that would ensure the inequality I'm looking for? Let's go to the table, and you read off the value for me. First of all, is alpha going to be greater than something or less than something? If I move alpha to the right, would that increase the area I'm looking at? Okay. So, as long as I find that boundary point, any alpha greater than that will also satisfy the inequality I'm looking for. Alright. So, what is going on here? There we go. So where is 0.975? Let me see if I can grab one of my pens here. There we go. Where is 0.975? Can somebody read off the chart? 1.9. So 0.975 is here. That means the alpha is 1.96. That's the second digit of accuracy. So that means alpha is greater than or equal to 1.96. This is from the table. I know it's sacrilege to look at tables in your day and age, but when I was younger, we used to look at tables. Alright, so this means that, now we plug in alpha. Alpha is 0.06 root n must be greater than 1.96. Right? That's alpha. Solve for n, please. N is greater than or equal to what? Anybody? Can you call out the answer? 1060. Well, it's technically 67.1, which you have to round out to 1068 because we don't have 0.1 persons. So that means you have to go out and poll at least 1,068 people to get the accuracy that you want. That's a far cry from 50,000. And it's much better than the 5,600 that we found with the relaxed accuracy using the Chebyshev inequality. So the CLT, without changing anything else, my accuracy is still 0.03. My confidence is still 0.95. But with the help of the CLT, we determined that all we need to do is go out and poll this many people. Yeah? So that's a good question. So the convergence of the CLT is actually, for most probability laws, is quite fast. The farther a probability law is from symmetric, the more you need to go. in terms of n to get convergence, but I mean by 1068 you're well past convergence. Yeah. Yeah. Practically anything of interest to us in the real world. Mathematicians come up with pathological probability laws that violate the CLT, but you don't really come across them in the real world. So this is what's awesome about the CLT. Without doing anything else, same accuracy level, same confidence requirement. Those are the specs of your pole. It's a design problem, right? You're designing a pole. And the specs are, I want 0.03, I want to be no farther away from the true mean than 0.03, and I want, with probability at least 95%, to be able to say that I am within 0.03 of the true value. So now this is much closer to what you would ordinarily see in polls when you read newspapers or read blogs or whatever. Any questions? Please get comfortable with dealing with these areas on the Gaussian. It's a nice symmetric curve. Figure out there aren't too many permutations of it. Either you're between these areas, you're less than something, you're greater than something, or you're looking at the tail probabilities. That's pretty much it. So get comfortable with how to read those off from a table. Question?
Switch back to
To the tablet. Oh, I'm sorry. I've been talking about... Well, thankfully I didn't say anything that really required. So, yeah. So really the permutations, like I said, are quite small. You're either looking at total tail probability when you want the probability that something is greater than or equal to some amount in absolute value, or you're looking at something less than or equal to something. You also should get comfortable with the probability that a certain random variable that's standard Gaussian is less than or equal to a negative number, because that's not on the table either. I don't want to go too deep into that because I've got to get to Markov chains, but what if so this is 0. Whoops, that's not the proper Gaussian. Let's draw a self-respecting Gaussian. What if this is my, let's call this beta. What if I'm looking for the probability that my standard Gaussian is less than or equal to beta, where beta is less than 0? How would you translate that into a probability involving the CDF? So these are the things you want to have develop the formulas for and keep staring at and practice with. Okay. I'm going to give you a break and then we'll start the next topic, which is Markov chains. Sure. Farther up? Or is that good? Okay. This is good? Down? That? Okay. Okay. Let's start a new chapter here. Suppose I live in this toy world of 4 websites in my entire internet. I'm going to number them 1, 2, 3, and 4. And with arrows, I'm going to indicate links that exist between each of these websites or nodes. I'm going to use these terms interchangeably. So I've got 4 nodes. It's essentially a directed graph, and thankfully you're familiar with directed graphs. I know that dark part of your past. So let's say this is my, did I get everything right? From the labeling, I'll know if I got it right. So let's say, so I've got a link going from, now that I don't want a highlighter, it's giving me a highlighter. Please. There you go. So I've got 3 links going out of node 1. And let's say if you're on node 1, with probability 1/3, you will follow any of those links. I'm going to forget about self loops here for now. And if you're in node 3, there's only one place you can go, and that's node 1. So with probability 1, you go to node 1. If you are in node 4, how many outgoing nodes did I draw for node 4? 1 and 2. So with probability 1/2, you'll follow each of these. And let's say with probability, and what about node 2? Node 2 can go to 3 or 4. So if you're on node 2 with probability 1/2, you will follow one of the nodes, one of the links that lead you to websites 3 and 4. Okay. I am, for example, interested in the long-term behavior of a population of people. Let's say I have a fixed population of people, and let's quantify that to 1. So I have a total of 1, whatever number there are. I'm going to normalize it to 1. And I want to know that if I wait long enough, what fraction of the population will be in node 1, which fraction in node 2, which fraction in node 3, and which fraction in node 4. And let's say I want to rank these web pages according to the fraction of the population that's going to be in what we call steady state to be found in any of these nodes. And the higher that fraction, I'm going to assign a higher score or rank to that website. This is one way to look at how Google PageRank works in a toy environment. What is the long-term fraction of the population in any of these nodes? If more people gravitate towards, say, node 3, I'm going to consider that as a more important node, and I'm going to rank it higher. There are many different ways to look at PageRank. Since its invention, there have been dozens and dozens of papers written about it. This is a probabilistic way of looking at it. So, this is an example of what we call a Markov chain, where we define it's a system or process, and I define a state for this system. So, I will say, come on, me black. Xn is the state of the system or process at time n. So time is a discrete integer valued variable. It keeps indexing forward, and let's say you're just one person. You start off somewhere at one of these nodes, and you hop according to some probabilities, xn equal to I means that we're in the ith state at time n. Or let's make it singular, so it's I am in. Okay? Yeah. I is the state. It's the node, exactly. So I am in the, sorry. I am at the ith node at time n. That's my the state of my system. Now, we define certain parameters for this. Pij is the probability that at time n, I'm in state j, given that at the previous time, I was at state I. This is called the transitional probability of going from node I to node j in one step. Given that at the previous time instant I was at node I, what's the probability that I will be at node j at the next step? Inherently, this is a conditional probability. Now, with Markov processes, this probability is the same as the probability of being at node j, given that at the previous time I was at I, and at the previous time after that I was somewhere, I don't know, and I don't care. E-I-E-I-O. Why not? In other words, the current state of the system only depends on the state of the system one time step prior. This is what's called a Markov property, this equality. In the continuous realm, let's go back to your physics courses. In the continuous realm, if I have a particle that's traveling in space, let's say, okay? And I tell you the position of the particle at the current time. Let's say the current time is t. I give you the position of the particle. Can you tell me where the particle will be one infinitesimal unit of time later? Is that enough for you to be able to tell me that? If all I give you is the position. Yes? No? So what's missing? The velocity. You can't tell. If I just tell you the position of the particle is here, you don't know which direction it's traveling. You don't know its velocity. So you can't tell me if it's going to go this way, and how fast, and how far. So I need to give you two things for you to be able to tell me what the quote-unquote state of that particle is at any given time. The state of a system is the minimal amount of information you need to be able to completely determine the behavior of the system from that time forward. So with respect to a particle, I need to give you the position of the particle, and I need to give you the velocity of the particle at time t. And if I give you those two things, do you need to know anything else about the past behavior or location or position or velocities of the particle to be able to tell me where it's going to go next? No. So the state of the system not only is the minimal amount of information you need, it also summarizes everything you need about the past behavior of the system. It encapsulates whatever is necessary from the past to be able to tell you how to go forward. So once I tell you the position and the velocity of the particle, you don't care where it's been, where it's come from, what it has done before. If it's been a naughty particle, you don't care. If it's been a well-behaved particle, you don't care. All you care about is where it is now and what its velocity is. That's what's happening with these Markov chains. That's a Markov property. So the state of this system, if I tell you where you are or where I am at any instant in time, which one of these nodes I'm visiting, you don't need to know where I've been before. Okay? From this point on, you can talk about my behavior going forward probabilistically. So if I tell you that currently at time n, I'm in node 1, you can tell me that with probability 1/3, I'm going to end up in node 2. With probability 1/3, I'm going to end up in node 3. And with probability 1/3, I'm going to end up in node 4. Okay? You don't care where I've been before. All right. Now, let's formalize some of this stuff. I don't know why this is not shrinking for some reason. Weird. So let's formalize some of our language. I am interested in long-term behaviors of these processes. Let's say I start. Let's say I have m states. Okay, so let's say m web pages. I start off at some node I, and after some steps I want to figure out what the probability is that I will be at node J. So in other words, I want to figure out these probabilities. I want to figure out what's the probability that I will be at node J at time n, given that I started... Oh, I need to draw this a little lower. Pardon me for a moment. Let me go up a bit. So I want to figure out what the probability is that I will be at node J at time n, given that I started off at node I initially. This is called an n-step transitional probability. And notice again, it's inherently a conditional probability. Okay. Well, there are different ways I can look at this. I can look at where I am, and so this is time n equals 0. Let's say this is time n minus 1, and this is time n. So let's just say 0, n minus 1, n. And I have m nodes. So this is the kth node, and this is the mth node. So how would I express each of these transitional one-step probabilities? What did we say this is? Probability that I'm at state j at time n, given that I was at state 1 at time n minus 1. What's our shorthand notation? Tell me what to write here. T 1 j. The probability that I will end up at j, given that I was at state node 1 step prior. So this is P, K, J, and this is P, M, J. Now, the process probably takes some kind of a trajectory to go from node I to each of these M nodes. What would I put here as a probability? P is only for single step transitions. R, I, 1 in n minus 1 steps. So there are different ways I can get from node I to node J. In n-1 steps, it might be possible for me to go from node I to node 1 and then do a one-step transition to node J. Or, ... I might transition from node I to node what? K in n-1 steps, and then in one step jump from node K to node J. Or I can go from node I to the last node in n-1 steps and get to node J in one step. Can you now tell me, based on this graphical representation, how I can represent Rij in n steps? What would you do with all these branches and numbers? Sum which ones? So, all the paths. So this path would have what probability? Yeah. Ri1 in n-1, and then? Pij plus Rik n-1 times Pkj plus all the way to Rim n-1 Pmj. And I can write this in slightly cleaner form, more compact, by saying over all intermediate nodes K from 1 to M. So this is my generic intermediate node. This node K right here. So this is essentially writing the law of total probability in a conditional universe. What's the conditioning event here? That I start off in node I. Everything is conditioned on my starting off at node I. So in this conditional universe, I can write the law of total probability. And so that would be that I will go from node I to node K in n-1 steps, and then in one step jump from node K to node J. This is an expression of what is called the Chapman-Kolmogorov identity. You can imagine I can actually draw this in a different way. I can start from node I and then say from node I in one step I can go to any of the nodes, and then from there in n-1 steps I can go to my destination. That's also possible. So there are different ways of writing these. So another way, alternative, I can start off in node I and end up at any of these nodes in one step. So this is Pi1, Pik, Pim, and then in n-1 steps, I can go to my final destination. So this would be R1J, n-1, Rkj, n-1, and so on. I can do that too. Or I can do an intermediate time step. It's all up to you. Now, one of the main questions, one of the underlying assumptions in the original problem setup that I talked about is that if I wait long enough, the probability of being in a particular state will have a limiting value. That's not always true. Okay, so one of the things we'll be interested in is, are there limiting state probabilities? Probabilities. If I have a two-state system, 1, 2, and I have this kind of an arrangement, do I have limiting state probabilities? That means that can you tell me if xn equals 1 as n goes to infinity exists? Let's say I start in state 1 at time 0. Will I have a limit? Can I be in state 1 at time 1? I start at time 0 in state 1. Notice these transitions must be 1, right? The outgoing probabilities, you're going to end up somewhere, right? At each time step, you're going to end up somewhere. If there's only one arrow going from state 1 to state 2, you don't have a choice. If you're in state 1 now, you have to hop to state 2. So, is there a limiting probability? Is it possible for me to be in state 1 at any odd time? So the probability just jumps around from being 0 and 1 depending on when, if n is odd or n is even. So no limit. There is no limit. The other question we have to answer is the initial state important? And these are some of the questions that I'll answer for you next time.